So sorry, guys.
Okay.
Um,
Glad you're here now.
so, okay, great. So I guess I'm just gonna ask you maybe to keep. I'll just go quick to kind of recover like some of this wasted time. So sorry again, guys. But
So,
anyway,
so Chavi, you should know
yeah.
we already kind of walked through and looked at the first like 5 slides.
Okay, so it's kind of all the intro. So we can skip that if you guys want. I mean, it's kind of more looking at some of these conceptual models, right, for separate fractal bedrock systems, and a little bit this idea of having these, separated like interflow and regional groundwater
Right.
flow that it's like showing on the slide.
And so
Um,
do you think, I had a question on this one, Chavi, do you think this is an appropriate model for us to be thinking about the flow paths in Luquillo? And do we have
um,
specific sampling points that we can use to characterize interflow and regional groundwater?
right. I mean, probably, this will be probably a better question for Sue and these guys. I mean, I'm not sure. I mean, I probably, I mean, I don't think it will be that different or like that, like kind of like I guess in this model, like that interflow has a larger kind of component than the regional. So I don't know if that really will be the case for us in Luquillo, but I don't know what you think or what you guys think. Um,
our region is obviously small, so we can't have a regional groundwater flow that is what you might expect perhaps in North America, at any site on the continent. But at the same time, we've got deep groundwater and we've got shallow interflow that we sampled
right.
often, and that's not actually incorporated into Sue's framework probably yet in terms of the shallow riparian wells that do capture interflow, and then our deep drilled wells that capture deep groundwater. So I think this might be plausibly applied to the data we already have in hand from
Right. Yeah, I mean, from what I understand, all this is mainly based on the shale hills data that Sue has, like most of
right.
this modeling. So yeah, I mean, I don't know. Obviously, the system is a little different, even definitely in terms even of lithology and all that. So it
Right.
might be quite different. But I guess, yeah, I mean, there's probably enough data to try to, run some of these models. But again, definitely Sue will be the one that will be more appropriate to answer this.
Right. Okay, so
Um,
let's move on to the next one. That had a key. Okay, we covered that. This one, yeah, I don't know. I think
so
we
yeah, I just
looked at
basically
that
like
enough.
talking about what Sue was saying, that some probably of this like separation of flows is mainly related to these mineral reaction fronts and these changes in permeability distribution, right? So like this idea of whether there is like these changes in permeability that might be just due maybe to some sort of pre-existing condition, whether it's like layering or fracturing, or it's like some more related to like these weathering reactions. Um, but yeah, it's mainly this idea on these reaction fronts. And then in the next slide, there is like this recent paper that Sue did on this conceptual model again for a hill, and it has like two layers of lateral flow, and same idea, right? So you have this upper layer um, uh, that is the soil, and then the bottom layer that is the unweathered rock. Um, and then the depth of the intervals of the water table fluctuation for both like the interflow and the groundwater flow are then these reaction fronts that are basically uh, related to these changes in composition and fracture density and porosity and permeability. Um, so um, So then, like, yeah, so what you are saying is that some of these hills might be kind of moving more towards like a steady state, where like the mass loss from these two components and the physical erosion become more like a geomorphological steady state, where there is really not much of a change on heat slope or even thickness of the regolith. And then, yeah, this slide is mainly kind of the same idea, but when you look more like at the whole cross section, where you also have these both like basically lateral flow zones and then vertical flow zones that are, again, like, you know, marked by these reaction fronts. And then, yeah, that's basically pretty much the same idea. So then we can just move to the next, because then the whole idea with all this is like that we have these big kind of like questions that probably can apply it on the next slide that will apply pretty much to all CZOs. And, you know, it's kind of follows in some of these recent work, especially like St. Clair's, and probably like, you know, like these three questions that I was like stated here, like whether, you know, like are fractures like opening at greater depth, like beneath the hill, that are the ones like starting the whole process, or do fracture opens because of these actually weathering reactions at depth, or are both happening at the same time because like some of these reactive meteoric fluids that are actually enhancing the opening of these fractures, right? So with all this, then if we go to the next slide, it's like, well, how then can we fit all this into Luquillo, right? We can move to the next. So then that's basically kind of trying to sum up. Again, I'm like presenting this. Probably, you know, the least appropriate, especially for you know, most of these 4 points that are here. I'm kind of trying to sum up the things you know, related you know, to focal area 1. So I'll just kind of go quickly through each one of these, starting with this idea of like reaction fronts, then moving into modeling this weathering advance in places with and without fractures, and how basically these fractures are impact weathering, and these are mainly based on like some of the modeling that Sue has been doing lately. Then I'll move more towards this part of more like the geophysics, which is looking more like the distribution of fractures. And then some last kind of component that Sue added at the last minute that wanted to show you guys that she was saying like something cool that we kind of discovered along the way, and it's like this significant subsurface particle transport that, you know, that we're able to see. So again, I'll kind of go a little quickly through each one of these 4 points. If we start with the first one, reaction fronts and flow in quartz diorite. And there is this kind of conceptual model, and obviously, you know, flow paths are not this simple, but this kind of shows the idea that there are multiple lateral flows in this like core stone routing zone, and this gives an idea again of these like reaction fronts under ridges, especially in the quartz diorite in Luquillo, that are kind of separated by this upper flow where there is not significant sodium and calcium from the feldspars, and then a lower flow path that shows like this more significant weathering of the feldspar. Right? So this is like a paper that Scott just submitted. I guess. I see. Yeah, you could just click all the way. Sorry, I didn't realize that it had the. And then, you know, the idea like that you can also see this in the deep volcanic clastic material, and that, you know, that formation of this regolith is mainly controlled by these very small small scale weathering fronts along fractures. And that's you know, some of like mainly the work that Heather has been the last few papers that she's been putting out. So if we move into how do fractals affect weathering, again, that relates to some of this latest modeling from Sue's group. And this shows like these models for unfractured hills, like 2 dimensions that show like this vertical advection as the mechanism for like solid transport. And it basically shows that decreasing the velocity of advection, basically it's going to decrease the thickness of the regolith, and then decreases also the thickness of this reaction front, basically as you go from this high to low flow. So then this next slide, if we go to this, and you can just click, I think that is like, yeah, click again, it should show, yeah. So it's like this recent paper that Sue submitted. So it will be the previous slide, sorry. So yeah, we're basically, so like they use models to look at the contribution of fractures in basically controlling the rate of weathering advance for a crystalline rock. So then you see the color scale where the warmer colors are showing this increasing extent of alteration, and then the blue basically will be like this unaltered granite. So then what you can see is that decreasing the fracture spacing, that will be like this D value, is causing increases in the regolith thickness, which is this capital L, and then increasing also on the reaction front thickness. That will be the small n, L. So yeah, if we go to the next, so we've been basically trying to use these models to then understand what is the distribution of core stones that are basically exhumed as a function of elevation, mainly in the quartz diorite, but also like in these volcanoclastics and cornfields in Luquillo. So if we go then to the third, like the fractal distribution, the next slide, in Icacos, and you can move to the next. So that's basically Joe's paper where we're like using mainly drilling and GPR like to develop this conceptual model. This was mainly based in the Rio Icacos watershed, and mainly the idea was to define regolith thickness and areas that might be more conducive than to fracturing. So it's mainly based, like in this case, like these electromagnetic wave velocities coming from the GPR, and then these drills, at these like specific locations. So if we move to the next, just very quickly, we've seen that GPR kind of like looks very useful to define changes in lithology. So we can see here like an outcrop, like the polar bear outcrop. So it's kind of a small scale survey, but you can see nicely how we can use then these changes in velocity. We're using both changes in velocity in the wave and also how the reflection record looks like, what is the nature of the reflections, whether they attenuate more or less, to then kind of define these changes in lithology and these like zones of increased fracturing, right? So then if we move to the next slide and we look at a larger scale, we can also see similar, how again like these changes in the reflection record are able to kind of define these areas that we think are, zones of enhanced fracturing, right? So in this case, we see like a much larger GPR profile, right? Almost like 400 meter long. So we see these zones where there is like enhancement or where like the reflections come up. And then also from other methods, we see these increases in magnetic susceptibility and decreases in conductivity. And then we're relating this to these areas where there is more fracturing, these enhanced fractures. So then if we move to the next, also just like to mention that we've also used other methods like this last campaign. We also just to kind of mention that we use also seismic and electrical conductivity, and we again can see like these changing patterns where we were able to detect these changes in the width of fracturing that in this case are coming from changes in electrical resistivity in the profile on top, or even changes in seismic velocity. We look at the profile in the middle, and then just all that combined with the GPR at the bottom. So we'll see these areas where there is this enhancement of reflections. That seems to be also the areas where this bedrock is coming closer to the surface, right? That it's shown by this resistivity and seismic. So again, if we go to the next slide, so then if we can zoom out and then try to put all this in a larger context, so we can then extrapolate it to this more like kind of kilometer scales, and then we see these increases in the width of fracturing as we move from a higher elevation to a lower. So as we basically approach the nick point, so so that kind of will be the take-home message, that the width of fracture of these fracture zones seems to be increasing as we get closer to the nick point. So then if we go to the next slide, that will be kind of a conceptual model for this fracture development that also, as related to the nick point, the positioning of the nick point. And so we can, the idea is that then the width of this fracturing as we get closer to the nick point is increasing. That's basically, taking some of these, or like the drawing is inspired by some of Gill's, conceptual models also. But the nice thing about this is that some of the stress modeling that we've been incorporating from Ray Fletcher, it kind of shows the same idea, and like the model on top, it's like this model for the minimum mass compressive principal stress. So mainly what the model is showing is there is a release of compressive stresses as you get closer to the nick point. So it's almost if you think about, almost like a glacier and how crevasses will develop in a glacier, right? So as you get closer to the edge of that glacier, there will be a release of that compressive stress. So crevices will get, will get wider, or will develop larger than, towards the center, right? So it will be that kind of same idea as you basically get closer to the nick point, then you have a more opening of these fracturing zones, right, closer to the nick point. So again, the conceptual model from the geophysics and the drilling and all this kind of matches nicely with the stress modeling from Ray. Okay, so then the last part will be this, what Sue was saying. What we discover for particle transport in quartz diorite, and this was this idea of trying to sample particle fluxes at deep groundwater seep, and we basically see these particle fluxes on areas right around the core stone. So the idea here basically is to compare these seep particles basically to different stream sediments within the area. So if we go to the next, so that the graph here is basically showing, so the next slide, the lack of basically sodium and calcium feldspar basically in the soil and the saprolite. So you see high sodium and calcium in these seep particles that basically will imply that they're basically derived from weathering bedrock and not from soil or basically saprolite, right? So if we go to the next, we basically also see that the size of these particles and the total mass increases with discharge. So then this graph on the left shows these threshold relationships between total mass of seep particles and then the peak discharge. So then we can see these particles that are sized between 420 to 850 micrometers that are increase basically more significantly when you compare to the other particle sizes. And then they're also like enriched in basically magnesium and iron compared to soils and bedrock. So it shows basically this differentiation between these two particle sizes. Okay, so then if we move to the next, so the idea is that basically then we think that there are these positive feedbacks between pre-existing vertical fracture zones. There are like these zones that I was just showing from the GPR and the geophysics, and these weathering-induced fractures, which basically are opening up because of this meteoric water input that happens above the nick point. So I guess the idea is that, you know, with all this, like you have these vertical fracture zones that are weathering hotspots and zones where sediment is getting produced, right? And then these positive feedbacks are producing core stones everywhere above the nick point, but are also basically responsible for developing these core stone filled valleys as well. Okay, so that's basically it for like this summary. I mean, just like to kind of give like a few, you know, final kind of points that it would related basically to these 4 main points. So first, like this idea that reaction fronts are separated by these upper and lower flow paths that show basically changes in weathering. For instance, we're seeing for the feldspars. Then the second, that this decreasing in velocity of advection and increasing in fracture spacing seems to decrease the thickness in the regolith, and then decreases also the thickness of these reaction fronts. Then all the geophysics part was showing that the width of fracturing zones increases with proximity to the nick point in relation to this release of compressive stresses. And then these positive feedbacks between pre-existing vertical fracture zones and weathering-induced fractures, and the idea that these probably fracture zones are actually weathering hotspots and zones of basically production of sediment. So yeah, again, I think that's basically pretty much you know the summary that we kind of put together for this. Again, you know, probably Sue would have been better to, you know, present all this, but hopefully I got the message across. And yeah, and sorry again for the, you know, delay. So I don't know if you guys have any questions or any comments or anything else.
Hi, this is Aaron. That's very interesting. I'm really sort of struck by sort of the way this sort of integrates across the whole landscape. It's very nice to see that tied together. And I'm wondering if there's been an effort, or maybe this could be an effort in the future, to sort of look at, like, even with respect to like the widening of the fracture zone, I might not use the right words, as you get closer to the nick points, and I'm curious if there's a way to try to connect that with the upper profile, you know, so that we could essentially begin to link across these different themes. And you know, how does that influence, for instance, the soil development or vegetation and that type of thing, you know, with this. So I don't know if you thought about that, or is there, to me that seems like it could be kind of an exciting way to approach.
So what do you mean, like with the upper profile? You mean like
well,
first?
Go back to your slide, maybe it might be easier if it's okay, Miguel.
Sure.
Which slide?
So like I go back one. Yeah, past the particle stuff. I thought was interesting. I have questions, but we could talk offline. But yeah, like that slide 24 is probably a good. Is that the one with the widening? No.
Like
but
the
that would be a good
conceptual
one to look at. Just look at the 24s, probably. Nope. That one, yeah, that's good. So I was just thinking, you know, whoop. Back to 24 is easier to talk about. So I was just thinking this idea of I don't know if I really captured fully, like when you said about how it gets, the fracture zone is wider. That's not really captured in this image, right?
Well, I'm trying. It's maybe the drawing needs some help, but I mean, yeah. If you look at the, so as you get closer to the nick point, like that, those double arrows are supposed to get thicker. So like the size of those double arrows is increasing. So see what I mean? So that
yeah, right. I see that. And yeah, so I guess I was sort of thinking about some connection. Obviously, your Regulus thickness works in the opposite direction as the width
right.
of the fracture zone.
Right, right.
But you know, I don't know like how. I guess I don't really have a hypothesis to put forward, but I'm just thinking about how that sort of structural, significant structural change across a landscape that, as you're drawing it across, from the nick point is relatively similar, same elevation, for instance. Probably the climate is likely similar, right? It's just proximity to the nick point. And, I don't know if that's, if there's been much done to look at the influence on I'm thinking plant community, right, is one sort of integrator of the effect on the soil, if you saw that, or other sort of, upper profile or upper regolith, if you want to use a non-soil term.
Right. Yeah, we haven't, really looked at any of those kind of connections, but yeah, it obviously will be great to, more related almost more like to the superficial, even like, even plant communities. I guess that probably, I don't know, I think Jill was also even seeing some, there is definitely some clear changes, right? When you hit some of these areas like where actually vegetation will develop, where you have like this, I guess he calls it coves, right? It's like so as you have like these geomorphological changes that you go from basically from the ridge to these coves, and like obviously your vegetation is clearly changing, right? Yeah. I guess from my understanding. So there is probably a lot of connections there that probably, I don't know, probably if you even take that figure and you zoom in, because obviously this is like, 8 kilometer kind of profile, but right. Probably if you zoom in into some of these areas, we have like kind of a massive amount of data that you can probably zoom in and try to almost, maybe even draw vegetation communities and try to see maybe what is the connection, between subsurface and those communities,
or even something like soil moisture might be another. Obviously, that's but that would be again kind of like an integrator that might reflect. And I don't know. We may have all that data, but it might be a nice place to do some sort of cross,
right.
or subgroup integration.
Right. Yeah, obviously we're, the good thing is like in the probably that from the geophysics perspective in the last probably year or two, we've been integrating a lot more, methods. Before we did a lot of GPR, and the problem even at the regolith is that it's not really giving you a lot of information because like it kind of attenuates a lot of the signal. So you may be able to capture the interface, but for that probably those first like few meters, a lot of times you don't get a lot of information. Now, when we bring these other methods, especially resistivity, that might actually, be more helpful for that, maybe to explore more like this, more like maybe, even 2, 3, 4 first meters of the soil that maybe, for instance, yeah, moisture could be something easily detectable with resistivity, you know, and maybe like even like these resistivity profiles, like actually the one slide that we have right here, you can see actually so that the resistivity is the image on top, right? So the main point of this profile is like, yeah, to look at the bedrock at this larger scale. But I mean, if you look at the superficial part, some might be noise, some might be effect of like, you know, that I don't know if it's like we should totally believe it, every single change that we see in there, but you can see a lot of patterns in there where you see changes in, you know, increase, decrease resistivity, where might be maybe related to change in moisture. I mean, you know, resistivity, for instance, will be very sensitive to that. So yeah, I mean, that could be, again, you know, like this, I think there's a lot more options opening for us for the geophysics especially perspective to kind of integrate more of these maybe more superficial methods or superficial processes from these other methods that, you know, it's definitely, yeah, it could be, you know, very interesting.
Yeah, cool. And we may have, maybe the data exists from in
Yeah,
some of these
yeah,
sites
again,
that we,
sure.
you know, I don't know. Like, so that's the only, I guess that's my comment, that I think there's probably an opportunity here
Right.
to do some integration.
No, I agree. I mean, I mean, we have a ton of data with the geophysical data. I mean, our issue is always the same, that like even at this profile that you see, like, okay, so we see this electrical resistivity cool profile, and it's like we have all this variability at the first few meters, but I mean, we need to constrain that somehow. So it's like, I don't know, yeah, if it's moisture, we kind of need something else to back it up, right? Whether it's like, I don't know, you know, some other kind of like, you know, direct information will obviously be ideal. But
Well,
again, you know.
So Jane and Maria are just chiming in via text. Maybe they're ahead of the game for us, but Jane is saying,
yeah, maybe I
what
can
do you want to comment?
read the Jane's questions. Where was the SEEP core stone site?
Oh, hold on. Where was that? Let me go to that.
Was that one of her questions? No.
Yes.
Yes.
Oh yeah, there it is. It's farther up, so I didn't see it.
I think it is like that Guava Valley. I think it's like the, there was some old like wells in that site, I believe, that, so it's like there is a map. If you go to the slide 26, there is a little map in there that shows, I think, the location. So it's like Guava Valley. See, so it was like,
Yeah, it's right before the Guava Valley, yeah. It's about
so
a
yeah, there is,
third of the way down the road to the gauge.
I think there is, there was some like old like wells installed in there, but obviously I don't think they're like really working anymore. But again, I'm not too sure. I don't know if you guys identify the spot on the map, basically.
Yeah, I don't know that there might be a well in the vicinity, but I don't think there are multiple wells. And it's not a well that we sample now. Whatever is might be there.
And then Jane says, "Oh, I missed that." And then she also, to comment on what we were just talking about, she makes a comment that all the codes are upstream of the nick points. And then Maria says, following up on Aaron's question, the shallow deep connections seem to be oxygen concentration and organic acids, which are modulated by biological reactions. So I don't know if...
Yeah, I think that's one, again, you know, that would be a question for Sue for sure. But I'm not sure if she was leaving any biological activity on the site for those models. And I think she made that clear on the paper, that I believe she was not considering those, I believe. But again, might be better for her to answer this. This is way beyond my kind of
Yeah, I mean,
understanding.
I was just again, and I just think it's probably there's an opportunity to do some cross-steam integration here, you know.
Well, I think you're definitely right, and that, as Maria's pointed out, that if there are bigger fractures and more regolith down deep, the water and the oxygen should move through there, and then we would expect to see, you know, that gives us a surface to deep connection. So I'm intrigued by, it seems that there are several testable hypotheses about what we'd expect for, I'll say, bulk water chemistry, and maybe some that we could develop for isotopes of various ions that are suggested by this interflow and deep groundwater, and then the fractures that are you know, compressed and below the nick point and sort of opened up above the nick point.
So there was one other question that Jane wrote. Did you speak about these results in light of the presentation Ray Fletcher gave last year?
No. The presentation he did, where he gave, where did he give the presentation? I mean, we've been, you know, he's been developing these models, right? So I'm not sure what he presented, but he, you know, he's basically the one developing all this. So this is basically strictly based on topography, right? So, unlike some of the details, basically are basically there.
Yeah, it was the compression.
But yeah, I'm not too sure what exactly he presented.
Didn't he talk about those fractures that are visible from, apparently visible from the topo maps of the aerial photography?
Yeah, he also talked
See the
about
one who
that.
talked about that?
Yeah.
Well, there is like there was like some, yeah, there were some like old maps. It was Parizek that kind of developed this, yeah, just like maps of fracturing, showing the fracturing and based on the aerial images.
Mm.
But I mean, it was mainly for anything above the nick point, or, you know, that's one thing that I'm always confused. So all the maps show all this fracturing right above the nick point. And then I don't know if there's just like nothing below the nick point, which obviously there is, because we can see that in the field, at least some fracturing below the nick point. But maybe I don't know if it's just like you don't see it as obviously from those aerial images. I'm not really sure. I mean, but all the images that he shows, like that we have from Parizek, it's always all above the nick point, you know.
So Jane, you need to buy a microphone, or I recommend the headphone with the earphones and the microphone all in one. A USB works quite well. They can work on a laptop, on a desktop. Anyway, Jane said she was thinking more about the modeling based on her the modeling talk, which I also do remember something about a modeling talk about this. And so the point that I would stress is that Aaron's exactly right. We need to try to put this stuff together. So I look at this image and I'm really intrigued. And I see, oh, okay, there's a lot of regolith and fractures and all this sort of action above the nick point. And in the Icacos, we see stream chemistry that's concentrations are much higher of all the weathering products above the nick point, and then they're lower below the nick point. Well, that kind of fits to me. If there's less fractures and less regolith, then presumably what's there weathering away and contributing to the stream solute load is less below the nick point, and that's what I see is less solute weathering product solute below the nick point. But that seems to be contradictory to what Jane's been telling us. So I still think we have these interesting contradictions that you know, that we need to explore as testable hypotheses for alternate scenarios about what's going on, the way this landscape develops and the way it imprints, the way the deep structure imprints on surface processes, stream chemistry, stream sediment transport, you know, because those are kind of things we care about from the critical zone services, ecosystem services standpoint. You know, what's in your water, sediment load in your water, how well the trees grow, and how deep and reliable your water supply is if you're, you know, in terms of wells and stuff. So I think there's a lot to mull over and try to put together
Right.
here with the other. And do we have, for example, so what would the implications be for the iron story that Focal Area 2 is spent so much effort, you know, detailing and with considerable success? That you know, what would we predict then about redox dynamics or iron or carbon storage as a function of redox and iron dynamics above and below the nick point in these soils, right? Aren't there some differences that we'd expect to see?
I mean, you would. I think the the most direct thing would be, again, this connection between the surface and the subsurface flows, right? That you know, if they're like, I'm just thinking back to the two like notches that Sue had on that one diagram, right? And that matters a lot for like these, you know, very humid ecosystems where you might have a lot of reduced iron present that could make a movement down in, you know, is there connectivity between that top flow and the bottom flow? And it seems like that would be modulated by these, you know, above the nick point, you should get, you know, a greater, there should be a place where these things come together and you get connectivity from the low flows and the high flows, or you get a more rapid like conduit, right, to the subsurface stream, you know, delivery system. I don't know if I'm saying that correctly, but and then the oxygen that Maria mentioned. I don't know if Maria, you have like if you have a microphone or not, but I mean, it would be good to sort of expand on what you were sort of addressing that a little bit. Although, do you have, Maria? Are you there? I keep saying that.
Yeah, Maria, please speak if you can. No need to just chat.
Okay, it looks like she can't talk either, but yeah, okay. That's too bad, but I mean, I think that, like, I don't know, Wendy just signed off too, so we're losing some key people in the discussions. But you know, the oxygen profiles down, like that would be one way to do that, to get at, I mean, we've done that in some places, but to do that a bit more, you know, systematically, to try to answer some of these questions about how do you, you know, how do these things change across as you approach the nick point. I guess I like that idea.
Yeah. And then the question would be, well, where could we physically, where can we work down there below the nick point? You know, I mean, there's two major nick points, I guess. I mean, there's the sort of lip of the Cocos nick point, and then there's the really big one that we went to on the field trip above the Hippie Pool, maybe, or wherever we went up on that totally cool place that I'd never been before. You know, on the coming up from the bottom of the Cocos.
Right.
And you know, it's not clear to me exactly, you know, how many practical places would we have to work. because it's, you know, we don't really have anything going on down there except the field work that James and Gilles have been doing, really.
Yeah, right. So I mean, I think there's some unexplored. You know, there's probably more detail here we could get into with a field campaign aimed at sort of integrating between these types of sort of things, the data that we're sort of looking at on this graph, and then the hydrology, and then the surface biogeochemistry, stream biogeochemistry, and then the vegetation distribution, which might be influenced by nutrients. Or it could be fertility is different as we, you know, I mean, maybe this is already known and we just need to integrate all the data. I don't know that.
The other thing that I would urge is I think there's some value in working in the volcanic classics where there are not these clear nick points, as again one of our null hypotheses is that, well, okay, where then when we don't have these distinct nick points, and there are nick points, there are waterfalls, but they're not as big a change in grade as the quartz diorite nick points. Well, then we should predict some uniform set of circumstances up and down below a waterfall, maybe.
Yeah.
I mean, some of these, I say they're not big, but man, they're definitely waterfalls that'll kill you. I mean, they're dozens, you know, they're dozens of meters tall. That you can't just like walk down them. You got to walk way around on the Sonodora, and less so on the Mamaeus, but especially on the Sonodora, there's some very large waterfalls that show up as little blips on the overall. It's also steep that they just show up as small blips.
So Jane is chiming in that she doesn't understand she says, I still don't understand the lack of impact of the nick point on stream chemistry.
Well, the lack of impact, well, I'm not sure I do, but if what we see is that where they're above the nick point, there's high on the Icacos, this slide we're looking at, there's higher solutes, and below the nick point there's lower solutes, but it's, I don't know if it's a linear decline, but it's a sort of a steady decline from top to bottom. It actually kind of mirrors that regolith thickness brown, sort of the integrated area of regolith thickness is actually follows the decline in stream chemistry or vice versa. And the volcanic clastics, in the Mamaeus, this is all finally submitted now in the Heineck et al. Tome, I'll call it. I'm an author on it, so I can call it something. It's a tome, you know, it's a whole lot of data. Anyway, in that Heineck et al. Submitted, there's the stream chemistry story is that it's what I just described in Icacos. High at the top, lower, lower, lower as you go downhill. Sonodora, it's unchanged from top to bottom. Sonodora, Espiritu Santo. So along that more hornfels rich face of the mountain, it's unchanged. And the Mamaeus solute weathering products are, you know, what the solutes we're talking about, it goes up as you go downstream. So 3 different patterns corresponding to 3 different lithologies. At least, you know, it would be good to verify that with multiple stream surveys. Obviously, I mean, it's only one stream network per lithology, so. And Jane saying that I would assume if there are more weatherable minerals at the surface downstream, you would get more solutes. Well, you would assume that. One should assume that, but it's clearly just not the case at all in the Icacos Blanco drainage. And so something doesn't add up. And so that's why I keep kind of pushing back on that.
So I was suggesting, and maybe Jane is agreeing, that there's not the water residence time maybe downstream.
Yeah, that's definitely a possibility. And
like
it's also, if it's steep because of the nick point has been broken through, or there's no nick point there, kind of slowing things down, that the stream hasn't worked its way through yet. So it's steep, so maybe materials just get, you know, between mass flow and erosion and earthquakes and whatever, landslide, that it's just material isn't there. I mean, that the regolith is shallow is what that picture that's still up on our screen shows, and that could explain it, right? I mean, to me, I see less weatherable stuff, less regolith in the one than the above and below the nick point. You know, less below, more above, but maybe I'm misinterpreting regolith.
So what is it again? The particle size and Javier, I know it was on like 3 slides ahead or 4. But that seems also to be very much connected to this discussion.
Slide 27, maybe?
Yeah, I think.
Yeah, that's odd. You're, for my version. Yeah, is this the one you're talking about?
Yeah, so help me understand where the nick point is here. That would be the seep, would be right at, is that?
No, the nick points are below all these points.
All these
Yeah,
points?
I think this, no, I think this is all above the nick point.
Right. The nick point's below, it's all above. So this is a comparison of the fresh diorite, the star, and then the particles. I haven't seen this before. This is quite interesting. So the calcium oxide to zirconium. And so the saprolite in soil looks like one thing. The small particles that are captured in this funky seep collector are something else, and they look midway between rock and soil. So
maybe go to the next one. There's another, the 128, which has that same diagram, but also has something else, Miguel, on it that might help. Okay.
yeah.
So these are not Javier, or I don't know who produced the data, but these are collected at different spots, or is this? I guess I didn't quite.
Yeah, this is basically Hyojin. She's not here. She's not on the top.
I'm
right?
here, actually.
Oh,
Hello?
so there you go.
Yeah.
You can. Yeah, you can tell them all about it, right?
Yeah, hi, Hoja. We can't tell who the phone, it's just unidentified phone caller, so.
Yeah, I had a problem with my audio system too, so that's kind of weird. Anyway, what was the question again?
Okay, so my question was just, you know, these were collected, the particles, they were collected from different, from the same location. There's a groundwater seep.
Mm-hmm.
It's this,
I guess.
this bucket, right? The seep?
Yeah, it's like a bucket that drips down.
Yeah.
Right, but
it
it wasn't like different seeps, right? Just
the
one.
same slip. Yeah, it's a kind of time series. So the filter bed was replaced every week. So the time series that you see, like peak discharge as a function of peak discharge, this is the peak discharge during these sample collection. So it's kind of the mass is like integrated massive samples that were collected during that week, and I selected the peak discharge during that week. So you see the kind of like threshold relationship between the peak discharge and massive samples. And I separated the particle sizes to see whether I see variation over the different peak discharge. And this is what I produced. So I see kind of 420 micron to 850 micron become like more significant as goes to the higher discharge. And then actually this figure, I had another figure that shows magnesium oxide to zirconium ratio, and this red section has more magnesium and then iron compared to even the fresh bedrock. So that allows me, kind of like suggest me that this particle has more biotite or oxidized biotite that can be related back to that deep weathering process. The biotite opens up the fractures and then, you know, kind of accelerate the weathering process.
So like one thing I would, Mike, one question I would have relative to our discussion that we were just having is, you know, if we did this, if you did this above and below the nick point, this is this is above, right?
Yeah, right.
But if we also did this below, or like as we approach it, or in some, you know, would we expect to see? I mean, I don't know. You tell me. Like, do you think there's because it could be that because the gradients are a little bit higher below the nick point, that we're mobilizing more large particles, which would not contribute to the, you know, the conductivity, right? Because they're not soluble. Whereas, I don't know, like that would be what would be one hypothesis that, what would you say to that?
So you're saying if I do the same thing above and below the nick point, what the difference I would expect or I would see?
Yeah, and particle distribution. Yeah.
Yeah, so I think, you know, I think the important factors to see the subsurface particle transport is actually fractures, like whether we have enough fractures to actually initiate kind of infiltration of oxygen and then force the organic acid to kind of oxidize biotite and produce subsurface particle. So I think below the nick point, since we have, I guess, less fractures, so the contribution of the subsurface particle, even though biotite would oxidize there, but there would probably no enough conduit to like push those particles out of the, you know, critical zone. So probably above the nick point is more significant, I guess, if there's more fractures.
Yeah.
And if I go down to below the nick point, probably it's less significant. The overall flux will be less significant. Yeah, that's I will guess that way, but not sure right now.
So that may be an explanation, Bill, for your observation, right? That you just don't have the weatherable, like surface area below the nick point per or weatherable volume is a lot lower, right, per hectare, right, or per watershed accumulated area, or I don't know what the right units would be, but
about the soil chemistry, if there's no not much fractures below the nick point, that means groundwater contribution will be smaller too. So that means, you know, above the nick point, groundwater to surface water or, you know, overland flow, groundwater contribution is kind of significant, but as you go down to the downstream, that groundwater influx is, contribution is smaller. Therefore, the stream chemistry would show rather dilution like trend.
yeah.
Yeah. So probably that all connected to each other, because whether there is a conduit or not, so that kind of shape a story, I guess.
Yeah, this is all really pretty interesting to me. I think there are some predictions we could make about solute chemistry and regolith depth and, you know, various attributes of the system above and below and the nick points. And, you know, with the other tributaries of the Blanco, the Savannah, and I guess the Kuboy, you know, and those are not inaccessible because of the trade winds trail. I mean, you can get to the headwaters of those without too much trouble. We could actually do, let's see if I don't know if the stream chemistry decreases. I know in all the tributaries of the Icacos and the main stem of the Icacos, stream chemistry declines with distance downstream. Concentrations decline. Well, I don't know if that's true in the other chunks of is that just an Icacos thing, or is that true across the quartz diorite more generally? Well, we could actually answer that question without too much trouble. And it's a shame Jane left because, Emma is not on this call, is she? I don't think so, because Emma's sampling in the coves. We could perhaps combine longitudinal stream chemistry transects with her sampling of the coves in the Kuboy and the Savannah.
This is Jamie. I got a couple more questions about this slide. Did you measure the amount of water that you collected each week as well?
From the seep, you mean?
Yeah, I guess you were getting it all in that bucket. You didn't overflow the bucket?
No, actually this peak discharge is really Icacos station, so it's not like direct representation of the peak discharge during that peak, during that week. So right, I haven't really measured the discharge. Yeah.
But just the total amount of flow. I'm just wondering if you get at a concentration, like a suspended sediment concentration in your bucket. Mm-hmm. So what I'm really getting at here is this amount of sediment, could it possibly be a significant contribution to stream sediment? If this is representative of groundwater discharging to the Icacos, could the groundwater actually be a significant source of sediment to the stream? It doesn't seem
possible. Yeah.
So if you had measured the water volume each week, you could maybe start to get a better handle on that.
Yeah, but it's kind of like coarse stone water seeping through. So I don't really know how to measure this kind of.
Yeah, you'd have to make a lot of assumptions.
Yeah. So.
Did you analyze the chemistry of the water?
Oh yeah. Yeah, I did. And then this thick groundwater has a much higher solid concentration compared to Guava, Rio Icacos stream water, and especially silicon concentration is quite high. And then the thick groundwater chemistry doesn't change that much with the function of discharge, Rio Icacos discharge again. So it's always
pretty constant.
High. Yeah.
But you're implying it has a different stoichiometry than the stream water chemistry, like a higher, relatively higher amount of silica?
Okay, sorry, I don't really get the question.
Okay.
What was it?
So the question is whether perhaps the silica concentration could be high. You say yes, it is high, and then is the ratio of silica to calcium to magnesium and bicarbonate, is that high or is that similar to the?
Yeah, I haven't really compared that. I just look through the concentrations. Oh yeah, that can be easily.
Yeah, it would be interesting to see if each solute is proportionately higher, each of the weathering solutes.
Yeah, we're just kind of always looking to see what's really contributing to stream flow. So have you discovered a new end member here? Is this sort of maybe a different, does this water have a different kind of chemistry that might be contributing to the stream at certain times that, maybe we've overlooked? Or does it just look like all the other groundwater? So yeah, it'd be neat to look at the data and the differences.
Yeah, I will take a look at the stoichiometry of the thick groundwater.
Thanks.
Well, it seems like we should be wrapping up then.
Agreed.
Okay. All right. Thanks, everybody.
All right, good to talk to everyone. This is pretty interesting.
Yeah.
Thanks, Javi.
Well, thank you.
All right, thanks.